Welcome to another edition of Electrolyzing Water with Paul Seaver. Today we're going to talk about IP, Ionic Product. Very few people understand Ionic Product. All chemists do, of course, but regular people like myself, we don't. If I wasn't exposed to electrochemistry, I would have no idea what Ionic Product was. So, plain and simple, Ionic Product is the amount of energy either applied to and bringing up, like in heat, or storing energy in water. So we'll just use a comparison of heat versus electrochemistry and leave the rest of them out of it. Okay? So there's other ways, you're talking about chemical ways of increasing ionic product pressure and other stuff, so ultrasonics. Anyway, so we'll just use heat to keep it simple because most people understand heat. Okay? So what's the difference between ice and boiling in regular water? Ice has zero IP, zero ionic product. That's why it's ice. It's a heavy structure of clustered water molecules, so strong you could drive a truck on it if it's thick enough. Okay? Now the opposite of that is steam, where water molecules are released, and at that point you're above 6.45 IP. And even in boiling, with creating so much energy, you lose your structure. You're structureless at this point, okay? Because all the molecules are separated. All right, so that's the difference in IP when it comes to heat. So now we'll talk about the difference in IP when it comes to electrochemistry. Now, everybody understands ice, everybody understands boiling water. So that's a real easy way to understand IP. Zero IP, watch that finger. Man, that finger, it always wants to come up. 6.45 IP. Okay, so there's our two ranges that we're going to work with. All right, so typical water coming out of your faucet on a typical summer day. Ambient temperature. What's your IP? Less than 1. I don't know what the exact number is, but it's less than 1. Okay? Now, the most well-known electrochemistry generators, alkaline ionizers for hydrogen water, that's a nano cluster. I don't know if we talked about the difference there. But so a nano cluster is a single polarity electrochemistry application which breaks up that single cluster at 13 to 15 molecules to an average of 5 molecules each. So now instead of one cluster, you have 3 clusters. Okay, so in absorbency, that means you increased your absorbency by 3 times. Okay, because in absorbency, there's during dissociation. So the reason that the molecules at ambient temperature are 13 to 15 is because it's always in a state of reconstruction. It's either losing a molecule or gaining a molecule. And so you'll never get a perfect 14, 7, 7. I don't have 7 fingers, so we'll have to use 5 and pretend they're 7. So you have even, okay, but it's 7, 7, not 5, 5. All right, and then once you offset, that's where your pH comes from. Either you go down to acidic or you're going up into alkaline. Okay, past that, because we're talking about IP. So now, in that constant state of formation, that ambient clusters, you losing or gaining 1 molecule at a time. So that's the actual molecule that you are absorbing into your aquaporins, because your aquaporins will only accept a single molecule at a time. So that's true absorbency into any kind of cell. Okay? So now when you electrolyze with a single polarity, you increase that by 3 times because you broke up that cluster into 3 different clusters that are all in a constant state of reconstruction because they're unbalanced. Okay? So no matter what, you're still unbalanced. You're still mixed acidic and basic molecules to make up that 5 molecule cluster. Okay. Now, when you go into dual polarity, what you have the ability to do is isolate the ions in their own environment, pure acidic, pure basic, or join them together for a neutral environment, single ion bonded neutral. which we'll get into that in another day, but today we're talking about ionic product. So the advantages of that, in your single basic, pure basic, you can keep a strong negative charge on each and every ion, eliminating clustering because like charges repel each other. That's ionic product, is everything that's leaving, okay? The actions of it leaving the cluster. Okay, so there's no clusters because everything's repelling each other. Try to stick two like polarity magnets together, it doesn't work. They always push each other away. So that's what you're doing there, okay? So you can have a pure basic that's controlled by a negative charge. You can have a pure acidic, which is controlled by a positive charge. Those are done in membrane separation and dual polarity. Or you can have a very specialized medium in neutral, which is patented, which joins one single basic and one single acidic ion together for a bonded neutral ion in dual polarity. And then to make it even more confusing, we can set the dominant charge. Okay, so for consumption in Esperer, the dominant charge is negative, of course, because we want it in the alkaline range. So once all molecules are reconstructed into neutral single molecules, here again we put a dominant charge on it, eliminating clustering completely. So the amount of charge that we use generally is 10 amps, and so at 10 amps what we achieve is the same thing you achieve with 200 degrees in heat, is 6.45 IP. Now one big difference is when using heat, pressure, or anything else, once you turn off the power source, your IP depletes. You know, pressure immediately, heat slowly as it cools down, ultrasonics immediately as soon as you turn it off, electrostatics, the same thing. I mean, there's all sorts of different ways you can increase IP, but the thing is how can you apply that IP and hold that IP? That's electrochemistry. Okay, that's what these generators do. And so the more pure that you can make the source, either pure acidic, pure basic, or bonded pure neutral, then you can stabilize it and control it, because Mother Nature doesn't have the power to come in and try to neutralize it. Now in neutral, you're already neutral. So that's almost stable indefinitely unless you open it and contaminate it. There's nothing to stabilize. So if you have something that's pure acidic or pure basic, somewhere down the line it wants to stabilize. Even if it's 10 years from now, it's still going to want to do it. So that's called shelf life. So the more stable you can get something, the longer your shelf life. So if you're relying on chemical reaction, heat, pressure, my RO just shut off. It must be full. And all these other things, when you remove the energy source, you remove the control. When you remove the energy source in electrochemistry by dual polarity with perfect balance, the energy remains stabilized. Now, that goes for low acidics as well as it does for high alkalines. Now we're talking about pH and IP, not necessarily the properties that are created as well during the process. Like the hydrogen, of course, isn't going to last very long because you can't hold it. And then on the bottom end, the ROS, it all depends on what we do with it at that point. What are we going to do with it? Are we going to bring it up to neutral, or are we going to bring it up to high pH, or are we going to leave it down at low pH? They all have their own stability. The lower the pH, the less stable. The higher the pH, the longer the stability. I make concentrates for that's similar to hyperchlorite. So I can't call it a hyperchlorite, especially not in this country. But it's very similar to hyperchlorite. We'll talk about it one day. I'm stable for more than 3 years. Try to get that out. Hyperchlorite's only stable for 2. So electrochemistry really knows how to organize and stabilize. So that's what happens during the process. You know, that's what these magic plates here do. People talk about electrodes. Oh, just go down to Home Depot, get a couple of nails and a battery. No. You got to have the right stuff. These are custom alloys. You can't see it and you can't tell, but it's got custom coatings on it. In this particular case, this one's for consumable water. So everything about this electrode has to be compatible with human consumption. It can't put toxic heavy metals in the electrolyzed water like some systems do. That's a whole other subject for another day. But I just wanted to show what an electrode is, okay? And so, you know, here's a chamber. And so it has a series of those electrodes. Every post you see is an electrode there. One of them's missing, that's the one I took out. All right, and then it has different pathways in there and other different components inside here. So then what it does is it runs through this chamber system like this, pumping in dual polarity, negative and positive charges, doing all its balancing. Typical electrolyzers work like this. They have an acidic on one side, they have an alkaline on the other. Don't pay attention to what I wrote in there. That has to do with something else. This electrolyzer works this way. There's one water in, one water out. So that's called acidulous. Acidulous just quite simply means the absorbency of salt in water or something like that. It's not a big deal. So IP, therefore, if you can stabilize your solution, your medium, your source into one polarity, you can pump as much of that charge into there as you want to because you're not fighting nothing. So in Nano, single polarity, they're only charging one side, so they can never balance. So when you want to, I don't think I have a diagram I can show that with. When you want perfect balance, you have to have power on both sides. You got your cathode, which is pulling everything that's coming in from the source that has a positive charge on it already. It's going straight to the cathode because the cathode's got a high negative charge, so opposites attract. There's a membrane in the center. On the anode side, you got a high positive charge, so everything that's coming into the chamber that's got a negative charge, bam, goes straight over to the anode. So with those two strong charges pulling and separating every component in the water by polarity, then flipping its polarity, that's how you get perfect. That's how you get perfection in water. And so if you're only running a single polarity system, you got water coming in that's got negative and positive charges. You're making an alkaline water for consumption. So you got a strong negative charge here. So everything that's coming in that's got a positive charge is going over there. But everything that's coming in that has a negative charge, that's what they're getting rid of on their wastewater. And then they're trying to tell you that wastewater is actually a sanitizer. No, it's not. But we'll get into that on another day. We'll get into that on sanitation and chlorine. So anyway, that's Ionic Product. I think this video's long enough. It's almost 15 minutes. It's just the amount of energy that you can pump into water. In our case, it's the amount of energy that you can actually store in water. So nowhere else, I'm going to make this claim right here on this video. Call me out to be a liar if you can prove it. Nowhere else in the world can you find a unit that can pump in as much power as our units and stabilize the mediums in all the different ranges. Say in acidulous, it's 5.5 to 10.5. With NCAL and the total range, it's 2.4 to 11.8. And then we can go beyond that once you start adding in electrolytes on one end or the other. So it doesn't matter where the range is, we can stabilize it at the pH that you want. That all has to do with controlling IP, controlling negative and positive, AC and DC, electrons and protons, however you want to put it. Once you have total control over those, you control the water that you're working. Welcome to Ionic Product. I hope I explained it very well.